So welcome everyone to this ARCHER2 training course. Thank you very much, Juan, for the introduction. My name is James Richings. I'm a member of the ARCHER2 CSE team here at EPCC. And I spend a lot of my time helping to support various aspects of the service. One of the things that's particularly of interest to me is GPUs, and as of January, we now have a small number of GPUs on the ARCHER2 service, and we're starting to do training courses around how to use them and different ways to program them. This course is going to focus on specifically yes, you should have been assigned a project. Sorry, just to interrupt that.
Don't worry, James. I'll
yeah, deal with that. Okay, thanks, Juan. So, where was I? We have so we now have a small number of AMD MI210 GPUs nodes on ARCHER2. It's 4 nodes. Each node has 4 GPUs. This enables us to start thinking about programming for GPU in the AMD space. Many people have been looking at NVIDIA hardware for some time. The Cirrus system that I mentioned in his slides, that has a large number of NVIDIA GPUs. But it's always good to have competition and different people looking at the same problem because it gets us best product. So we wanted to have a balance of both available. The other thing I just want to say on course setup before I go into any more detail is we also have this Etherpad for typing notes, which gets highlighted with different contributions. So as we have a scrolling chat going, if things start to get lost there and stuff you want to come back and answer questions on, if you type notes here, we'll be able to track them more easily and come back to you. So this is linked as the course chat on the web page for the course on the ARCHER2 website. And we can interact with you here as well if things start to get lost, if there's a lot of people talking, given that we are a reasonable number of people today. So to give a little bit more introduction about what these GPUs actually are on ARCHER2. So this is what a GPU node on ARCHER2 looks like. You have 4 GPUs and they have some fast links between them in blue. And they are connected to a AMD CPU, and this has 32 GPU cores. And then we have some links out to the network, to the other nodes off of the CPU. So you can communicate quickly between GPUs and slower out. And this is the model you tend to see various hardware that you have this hierarchy. Specifically what's sort of in each of those GPUs, just to give a bit of a schematic, this is what's contained. There's a bunch of the sort of normal sort of memory type things, there's some fabric type things that are linking stuff together, and there's a number of compute units. And I'll come on to this diagram a bit more in future, but basically this is what we're going to be operating today and discussing in detail. Now the overall, you can't see the shared screen. Anyone else having problems with the shared screen?
I can see it. Could we just try to restart the browser? Sometimes it happened to me that I needed to restart the browser and it works. So sorry about that.
Zoom in a little bit. I think everyone else is okay. Yeah, okay, thanks, Kevin. So we'll come into the details of what these different parts are later. This details on the AMD website. But give an overview of what we'll talk more generally about today. We're going to start off with 2 lectures sort of on more general theory and the model for GPU programming. And then we're going to start looking at some examples. And the flow of the rest of the day after 11 o'clock will be, we'll discuss a particular aspect of the programming model. Broadly, while we're talking about HIP here, this should apply to CUDA pretty well as well. And we'll discuss the choices that AMD have made in their own API. and there will then be examples. And what will happen is we will use an example and then build on it for the next section, but you'll kind of have the solution built into the next bit. So if stuff gets confusing or feel like you've missed a step, please ask questions. But there are solutions available to you, and we can discuss them through as well as we go. Okay, that's all the prep I wanted to say. So starting off, so initially, what's sort of our very simple model for performance on traditional processors, we have kind of four main sort of controls here, or four sort of key factors. We have some processor, and we have some memory, and they have a way to interact. And the factors that sort of dictate performance here will be things like clock speed, the rate we can issue instructions to the processor, memory latency, the time it would take to retrieve data from memory to the processor, the memory bandwidth, the amount of data we transfer in a particular unit of time, and the parallelism. Can I replicate the basic unit above, and how do I arrange this organization so that I can process data quickly? So processor clock speeds to determine the fundamental rate of processing instructions and hence the data. So this is kind of what's dictating really our limit on flops. Historically, we've sort of got increases in CPU performance by increasing the clock speed. Okay, that was a while ago now. But basically, because we end up with power constraints, most of the modern processors have clock speeds between 2 and 3 gigahertz. So ARCHER2 for the CPU nodes, actually, I think the boost clock speed is up to like 2.8, but the sort of high is 2.2 gigahertz, and the medium clock speed is about 2. We've looked at lots of studies around how we can look at energy efficiency of the system by altering this frequency and setting it for users, and there's controls there for that, and what the trade-off there is. And we'll come on to why a little bit more about that in a bit. Memory latency is a serious concern. So how many clock cycles does it take to go retrieve a piece of data from memory? And how long is the process idle waiting for that? So CPUs try to mitigate this problem by having caches. So the memory that is closer to the processor is thereby is trying to get as close as possible, reducing the latency to access. You have many caches in a hierarchy, and they're typically referred to as level 1, level 2, level 3. Right. So as a first little exercise, can everyone log into ARCHER2 and run LSCPU on the login node and just get a sense of the information it provides and try to identify what the different cache sizes are for ARCHER2. I think it's a little bit small. If someone who's fast wants to ping the answers to the chat. Yeah. Okay. Yeah, fantastic. So so we have some level of hierarchy, and we're able to probe this information on the system. And this is trying to smooth out this access latency, really. That's what you're attempting to do. And we'll contrast this when we discuss the GPU nodes in a moment. but it's a point to sort of like baseline what our expectation from a sort of a modern CPU is in terms of the size of these things. Okay, so we also have memory bandwidth as a consideration. CPUs generally have commodity DRAM or dynamic random access memory. All the size of this memory can be in the order of hundreds of gigabytes. So on ARCHER2, for example, we have nodes, most of the compute nodes have got 256 gigabytes of DRAM. There's some high memory nodes with twice that, 512 nodes of RAM. It's really around a cost sort of, cost is usually a determining factor. This is very expensive for high performance memory. And the maximum memory bandwidth is usually limited into the order of sort of 100 gigabits per second, sort of the commodity hardware. And this is actually really usually one of your limiting factors is this memory bandwidth. So if you've ever profiled your code and looked at what's called a roofline plot, unfortunately I don't have an example to show right now. Effectively, this tries to compare if you're limited by your flop performance or your memory bandwidth. And you'll see that for the majority of codes, the memory bandwidth is the thing that's limiting, that they're not actually able to access all the flop performance that's available on a processor because they are not able to access the memory that they need to get to quickly enough, the data that's stored in memory, so more actually quickly enough in order to get performance out. So once we so going back to our discussion just on clock frequency, once we hit a limit where we couldn't really increase clock frequency because of the power requirement, what we started to see a trend of is increasing the number of cores, or using more processing units to try and increase overall performance. So what we now see is nodes and chips with many more cores, and this sort of, you saw this sudden switch from very high frequency single core designs to lower frequency multi-core designs, and this required a change in how we program. And this is where you could go down sort of for performance and CPU, start to discuss into OpenMP and thread parallelism. And for those interested in that discussion, we run courses on that very regularly. And I think one of the always open courses that one just advertised discusses that. So for those interested in CPU parallelism, that's where you go. And it's kind of, this is a little bit in what we discussed today is a little bit analogous to that, how we do something similar on GPUs. So some of the themes there, if you've understood that, will be similar. And if we run the same LSCPU call on ARCHER2, can someone find me the number of cores on each node? From the same output that you've already generated, if it's still in your terminal. Any other guesses? Yeah, 128. Okay, so this is a common issue with counting numbers of cores on CPUs is we have hyperthreading in CPUs. I'm not going into detail of that, but often these tools report all the hyperthreads and they're not actually physical cores. So the answer is 128. ARCHER2 CPU nodes and the logging nodes are the same. They have 2 sockets, each with 64 cores each. And this allows us to do a great deal of parallelism. Actually, and it's quite a high number of core count. Really, you can look at comparative systems in the past, and it's much below that. I'm trying to remember now what Archer was, but I think it was sort of half. And AMD especially offer a range of core counts going down beneath this per socket. One thing I did want to just say, actually, before we go any further around this, is that this is the ARCHER2 documentation. And if there are issues throughout the course, this is a good place to look for information to help you with debugging. There's both this description on hardware. I just showed a little diagram of what the CPU nodes is. Sorry, I should make this bigger for everyone. We also have some notes on GPU service as well, part of the service. So we have a system that we're going to use a lot, which we're going to access the compute nodes via some slow batch system. But what I wanted to show is what a modern sort of CPU node looks like, as we've just been discussing it. It looks actually quite complex. We have our 64 cores on each of our sockets. They're grouped in groups of 8, and you have some hierarchy where each of these different groups have some form of cache. So you see these little blocks of 8, and they have different levels of cache in them. And this is the hierarchy we were talking about a moment ago. So these all combine to give you a performance system on the CPU side, but that's hit limitations basically. Let's go back to my slides. At some point, you struggle to fit more cores with the right ratio of cache in, and then you want to do something else. So where do you go next? And the other issue here is really a limit. You start to have a limitation of how do you get the power into more cores, and you hit a limit there too. The other thing is to really highlight is that often in high performance computing, we kind of end up with being driven by what the wider market is doing. We don't have a luxury of designing dedicated hardware. Anymore. There have been efforts in the past, but it's very expensive to do this, and getting engagement from large tech companies can be a challenge. So what we often see happening is we need to take look at what our wider market is doing, and in the graphics processing case, this was computer games. Kind of had a massive commercial interest, and you had many core processor that have been developed for these purposes, for processing basically pixels, but they're subject to the same discussions and hardware design choices we talked about above. We have limitations on power, clock frequency, and we need to get our memory to the location to do the work in a quick way to be efficient. Okay, I'll leave someone else to discuss that off-topic question, but I'll discuss it in a bit. So then the question becomes, how do we sort of effectively utilize these? And that's the program models we can discuss today and tomorrow. So clock speeds in GPU. So let's talk about our sort of key metrics for performance we've been discussing in the context of GPU processors. Clock speeds have historically lagged behind CPUs when you're talking about graphics processors. They're now more broadly similar, but the performance benefit you're getting from the GPU is related to the parallelism, not the clock speed in terms of the flops you have available. So, for example, I discussed earlier that the ARCHER2 CPU nodes, they'll be running at around 2 to 2.5 gigahertz. If you look at, as I have the numbers off the top of my head, graphics processors are around 1.4, so they're comparable, but they are slower. The memory latency problem has not gone away, but the way that graphics processors get around this is they are actually not trying to solve it so directly. What they're doing is saying, if you oversubscribe me with a lot of work, and I have a way of switching between parallel tasks which are independent, then I can hide the latency more effectively. And that, if you've ever listened to some of the talks by NVIDIA on this, they often describe these as GPUs as throughput machines, and you are the CPU as a system designed to minimize latency, whereas a GPU is trying to hide latency and get high throughput calculation. The other thing that GPUs really invest in is they have very high memory bandwidth. So they have relatively small, order of tens of gigabytes, but massive bandwidth. So this is order of 1,000 gigabits per second from GPU memory to the GPU cores. So this allows you to better balance this supply of data to the available flops, and it allows you to get much more performance out of the hardware. But the sort of balance here is that you now have significantly more parallelism to deal with. From the programmer's perspective, you have to marshal more threads in a sensible way. So you kind of put the onus on the programmer to kind of marshal this potential performance, and there are ways you can make poor choices in that sort of marshalling. So a little bit of terminology. Cores on AMD GPUs are organized into units referred to as compute units. So each compute unit contains several smaller sort of processes called streaming processes, and these processes are responsible for performing mathematical operations that are required for tasks such as rendering graphics, encoding video, performing scientific calculation. Okay, we see the same cores. So, for example, the AMD MI210 GPUs that we have on ARCHER2, these have 104 compute units, and each compute unit hosts 64 streaming processors. And this means that in total you have got 6,656 streaming processors to work together. So for a more complete overview, you can look at this particular link, but I will just use this to go back to the diagram I flashed up earlier. That's not what I wanted, this one. So you can see that we have these compute units, and inside those you will have a number of streaming processors, and you've got a lower sort of cache hierarchy here, and you're trying to marshal all of these compute units to work on different data independently so that you can switch between the data effectively. So a little bit more discussion on the hosted device sort of picture that's going on here now in sort of practice. What does a GPU node end up looking like? So if we take a slightly simplified case where we have a single CPU and a single GPU on a device, on a node, and each of them has some memory, and usually, so we think about the GPUs are hosted by a standard CPU. There's nothing special about the CPU. It's what you'd expect any other part of the system. It's responsible for orchestrating the GPU's activity. So in this context, the CPU is referred to as the host, and the GPU is referred to as the device. So you have this concept of host side, device side. Each of the CPU and the GPU have some memory associated with them. And what you tend to see, although this picture is slowly changing, is that the CPU will have a small number of cores and a large amount of memory, but with a relatively slower memory bandwidth. So this is this order 100 gigabytes here. It's the memory bandwidth between the CPU and the host memory. Obviously, caches will end up being faster and things like that. You then separately on the GPU side, you have many cores and very fast access to memory, but the overall size of the memory is smaller. Now, this size of memory, just to give you some general idea of trends, is on the GPU side is growing. you're now getting the latest NVIDIA Hopper GPUs, you're getting up towards 100 gigabytes per GPU. But the critical design consideration up until very recently, and this is unlikely to change in a broad sense for a while, is that the connection between the two memory spaces is slow. And this is your bottleneck. Moving data between CPU memory and GPU memory is order sort of 10 gigabits per second. This is the slowest link in the system, and this is the thing you need to consider if you're worrying about performance, is minimizing this transfer of data between the host side and the device side. The absolute bleeding edge as of released December time, there are some new technologies which increase this host device transfer up to the order of 100 gigabytes a second, but the rate of rapid deployment of those may take some time. So, and even then, you're still better off accessing, for now, very quickly from the GPU memory itself. You're still going to have more bandwidth there to do things effectively. Let's think about anything else I wanted to say here. Yeah, so I'm just going to go to, now we've discussed this, I'll just go back to my picture of the ARCHER2 GPU node and explain in a little bit more detail that in some bit more context. That's not what I wanted. So if I just focus on this on the, should have got a better picture of this. On the right here, in this case, our CPU is this AMD EPYC. It's a Milan. It's got 32 cores. We have this red line that connects our GPU via some interface, which we're calling switch, to our CPU. This red link is slow. This is our order 10 gigabytes connection to our GPU. And with the blobs, I'm saying the GPU and the GPU memory are in the blob. Same with the EPYC CPU. I've got a CPU and its memory in the blob top. What we may come on to later tomorrow is discussing how we connect between the GPUs, but what you're going to be using often during this examples is you'll be sharing a single node so that we get basically there is enough access for everyone to do something as we do the examples. We're not expecting from the examples to hit massive overheads from that because the scheduling system will partition out the CPU resource evenly to each of the users of each of the GPUs. But you can start to see how this builds up. If you then go multi-node, you need to make sure you're connecting and passing memory around effectively. So often people invest money in making links between GPUs fast as well, so that you never have to hit the CPU. Okay, I've talked a lot there and tried to give a brief introduction about the structure of this program. Any questions at this stage before I move on to the next section and a bit more about programming models? Okay, I take silence, meaning everything's completely clear, which is probably dangerous. Yes, they can be underutilized, and this is a potential risk. It's not a risk, sounds a bit harsh. I think what I'm trying to say here is that you need to profile to make sure that you're using your GPUs effectively. And there is always opportunity that you underuse GPU. Because if you can't get enough useful information into the GPU memory to work on, then can the GPU effectively use all its cores and all its power? So what you've seen a trend is the GPU memory growing so there's more available data to work on. But usually what you try to do is have a problem that's sized more for the GPU memory, that's going to sit wholly there, that can be worked on and iterated on maybe, and then only a few bits come back. Okay. Okay. Yes, there is. So find the correct thing I want to show that in, and I will show that right now. I'm just waiting for some resource to be allocated. Okay. So I'm just going to increase the size of this terminal window. Okay. So I'm on GPU node on ARCHER2. It's going to do something we will discuss in more detail in the first example. So I have asked for, let me just go through this again. I'm doing what's called an interactive job on the GPU. And I am logged into the GPU node. I've requested a single GPU and I've asked for 20 minutes. We'll discuss quality of service and things like that in a bit. And I've just got batch interfaces. So one of the most useful commands you can use for probing the GPU information, a little bit like LSCPU, is this ROCM SMI. Commands. I'm trying to remember. I think it's, and that's zooming in, really not helping anyone there. And you can start to show information about the GPU from that. I have put some of this information in the documentation. On the ARCHER2 documentation about what the results are, but you can use this to probe information about the GPU itself. I'm trying to find the one I want to show. It's probably going. Let's try to show them. See, I've got one device and I've got some information about clock frequencies. I've got temperatures. I've got other details about the GPU, and that's something you guys can play around with yourselves. Just consideration for time, I want to move on to the next lecture, but maybe later we'll get a chance to look at this a bit more. In some of the exercise submission scripts, you can see this in action, because it is the first thing that's run in when you submit a job. Next question from Jim. So are there subtask GPUs that are just unsuitable for them, performing a small number of operations on a large amount of data? Or, yeah, so what you want to do is it's fine to do a small number of operations on a large amount of data, as long as you can duplicate you can parallelize the operations so that multiple elements connect at the same time. I'll kind of answer that in this lecture, so I will move on to that first, and hopefully it will be a bit clearer about how we go about programming them and the answer to that question. Okay. So programming models. So we've got some hardware that's got very fast bandwidth, and it's got a lot of cores to work on some data. So you don't really want to worry too much about the decomposition of cores or compute units, or whatever the hardware is doing. You want an abstraction for that, so that the GPU itself can organize how it's going to execute parallelized bits of the code, and it can do something that's hardware optimal, and you just have to worry about making sure that you get the data that's being operated on for what you need to do. So if we have a one-dimensional array, we can think about decomposing this into individual elements that individual threads are going to work on. So you could say each element in a standard sort of C-type array has got some data I want to just double, and we'll see this in the next example. I'm going to give thread 1 the first element, and then thread 2 is going to get the second element, and then thread 3 is the third, and so on up until the number of threads I have. And they're each going to be able to operate on that piece independently and do some operation, and that's going to be able to exploit the vast number of threads that are available to the GPU on the GPU. We can also think about blocking this up into groups. As a working group, or in CUDA parlance, this is a block. It's a collection of work items that are going to be scheduled to run on a single compute unit. Remember, each compute unit has a number of threads, number of these streaming processors. So your one-dimensional picture might be chunking up a standard array into blocks, and then in each block, the particular thread on a particular compute unit is going to operate on them. In AMD parlance, this is a wave front is a subset of one of these working groups, and it's designed to execute with sort of single data, single instruction, multiple data. So you may also hear this referred to in a new way in terms of single instruction, multiple threads. So each one of these wave fronts consists of 64 threads, and the wave fronts are kind of mapped to the compute units for execution by the hardware scheduler. And what you're often doing is you're, as developers, you're selecting a number of wave fronts working groups, and this is based on the problem size. So what you're trying to do is work out the optimal blocking of the structure so it can be distributed to the compute units for your particular problem, and that's going to depend on the problem size, and that will allow for efficient operation. But the main thing here is you need to have them to be parallelizable, and they need to be independent. And if you start having dependencies between different sections of the array, then there's going to be some serialization. And the key thing in the exercise we'll discuss is about how do we keep things nice and parallel and separate, so different blocks can be executed on different regions of the hardware. And because the background of this is, sorry, let me just answer that because this is an important point to get clear. So I think it's more that your blocks consist of groups of threads which are acting together with a single instruction. So a wavefront is one collection, but then each individual, get this the right way around. the compute unit should have a single instruction and multiple data to act on. So each thread in a compute unit is going to get the same instruction. And a wavefront is just saying there are up to 64 threads acting the same instruction set together on a series of data. And how you size the blocks to act on relative to this wavefront size is going to change your performance characteristics. And this is really going to come into what's happening with sort of the cache sizes in the hardware. So I think I just want to introduce the wavefront concept and not confuse it too much about the blocking structure. What you're really trying to say here is I have the same instruction and I'm going to divide my data up to each thread gets its own bit of data and they're going to act with the same instruction, but the blocks allow me to move the data that's being to a particular space in hardware, all being done the same operation at the same time. That helps to clarify. So obviously, these models were originally designed for graphics processing, so two-dimensional, and actually, when we're interested in physics problems, we go to higher dimensional cases. You have three-dimensional versions of this. But you start to want to decompose a two-dimensional problem in some Cartesian picture, and now you have sort of an X and a Y blocking of some problem up into threads. So your arrangement of work groups, blocks, is referred to as a grid. So you have a grid of blocks, and each block has threads. And these blocks get passed to a particular compute unit, and the threads in there operate on the data in the block. Yeah, and this can be extended to 3 dimensions. So we'll discuss this in the examples next in more detail, but it then becomes very important about which way you order thread access to a particular data. So you have a concept of a fastest moving thread, which is going to be the X thread, and that has to make sure you're accessing memory that's contiguous, because you want to pass a single line of data from memory into a particular compute unit. Every single thread in that compute unit accesses the data one by one. They do their operation, which they've all agreed to do on that set of data, and then they move on to the next set of data in the next instruction, and go like and chunk through like that. And we'll discuss the exercises to go through that in detail. And that's kind of the key thing to get out of this discussion today, is this concept of blocking your data up so that the threads have contiguous access, and this is the big change from your the way you think about this on CPU. Okay, so when we're going to program this, we're going to use for this example HIP. This is very similar to CUDA if you have experience with CUDA. HIP is so I was going to say something else. There are other programming models on the ARCHER2 documentation. We've tried to give a variety of programming models. There's some things with OpenMP offload and other models. You can also just call some libraries to get some performance, but there's this hierarchy of your ability to express the detail of the problem that you want to solve. And this lower level programming style gives you much more control over that, but you have to deal with the complexities of organizing your data yourselves. So HIP itself stands for Heterogeneous Compute Interface for Portability. It's a runtime API. And kernel language implemented in C++, tool enables developers to create applications, protocols, AMD accelerators, and also target CUDA devices. The reason it can do this is because AMD were kind of following a bit behind NVIDIA in terms of their CUDA development and have a very similar API. It is behind what NVIDIA are doing, and the level of functionality is trying to keep up, but in some sense it's good because they're taking a similar approach to the same problem, which means there isn't an entirely different way to learn necessarily, and the concepts are generally similar. Yeah, OpenCL should be able to target multiple different architectures, but the question there is I don't have much experience with OpenCL myself, so it should allow some portability, but how much support there is for newer features is a question. How much performance does it give you? There are other things as well. You have OpenMP offload, you have specific APIs, and you have things like C++ standard parallelism, which is also coming in as well. And there's a wide landscape of these, and there will need to be a consolidation, but you've got a spectrum between something that looks very directives approached and something that allows you kernel level control over your problem. Yeah, so HIP is allowing you to target AMD GPUs. It also allows some support to target NVIDIA GPUs. So there's a bit of portability built in there. And then CUDA is primarily for NVIDIA GPUs. Right. HIP has two distinct types of source code: host code, device code. The host is essentially the CPU. It executes the host code on the CPU. This has a typical C++ syntax and incorporates sort of the standard features you'd expect. The entry point for execution is the main function. You can utilize the HIP API within the host code to facilitate various tasks, such as generating buffers for memory on the device, managing data transfer between the host and the device, and then initiating the execution of device code. And we'll talk about how those calls work. The device, typically the GPU, executes the device code itself. So it utilizes a C-style syntax, where kernels are used to launch device code. Instructions from the host are queued into streams for execution on the device. So this is asynchronous when you're executing device code. And we will talk a little bit about the fact this is asynchronous and the fact that you have to make sure that you're happy that everything is finished on the device before you can start using or pulling back results from the device to the host. And there's synchronization tools for that we'll go into. Okay, some basic compilation bits. So HIP-CC is the compiler driver utility that calls the AMD LLVM compiler to compile the HIP code. It's complete. This HIP-CC is included in the AMD ROCm software stack. So the HIP-CC utility compiles both the HIP code for GPU execution and the non-HIP code for the CPU execution. It defaults to the AMD Clang compiler. Other compilers can be used for the non-HIP code, and object files can be linked accordingly, as you'd expect. So on ARCHER2, to get access to this compiler, you'll need to load in some modules, and we'll discuss those in the first example after the break. To compile, you call HIP-CC, then this -x HIP bit, and then your code file. What the -x HIP's doing is just telling it to look inside the .cpp file and compile the instructions from in there. It's not expecting a separate the kernel code for the device to be kept in a separate location. To see exactly what's being passed, what HIPCC is passing to the compiler, you can use the -- verbose option to get more detail and print out all the various flags that are being added. The other thing that's important to flag here is that you will need to specify what's called a compute capability. There's a module in ARCHER2 that sets an environment parameter, so this doesn't need to be set explicitly, but you can also pass it in by hand. It's basically saying what generation of GPU have I got, what's its functionality, what does that mean for how I am taking this block and thread structure and distributing it to the devices available to me. For this particular one, it's the correct one for the MI210s, but beware that if you're on different devices on different systems, this code will change and there will be advice and documentation about what it should be. There's also documentation on the AMD website in order to provide the set that you should be using. The other thing to highlight is that as I was saying, CUDA has been under development by NVIDIA since 2005. AMD is rather late to the party and develops HIP. It kind of shadows CUDA and has very similar sort of type replacement type syntax. So while this will, but the warning here is not to assume that this will perfectly port your code by just going through your program and copying to replacing CUDA with HIP. There is a tool that allows you to do this, which we won't go into a lot of detail today, but called Hipify, that allows some capability to help migration. It's not perfect. It does generate bugs, and that's a single direction transformation. And there are other tools available in development to do something more generic, but they are very much active research projects with some public functionality, but mileage may vary with them. I think that's all I wanted to say here. So we will take a short break now, but just to summarize, sort of the goal for the programmer is to describe the problem in the abstraction of grids, blocks, threads. The hardware is then free, because this means that the threads are doing independent work to schedule this work as it sees fit. It can distribute this over the compute units and its various wavefronts in order to get the optimal performance. And it's going to do things in the background to switch in and out processing in order to hide latency for you. And that's going to allow you to get very high performance on these pieces of hardware. This is the very basics, and what we'll really go through today is start building up that functionality. So the next example, we'll just look at moving memory around. So I need to double check it, but if I remember, what it's doing is if you don't include it, it's expecting there to be a .hip file with a particular code included in there, separate from the .cpp file. And what it's saying is, don't go there, check the before I get this wrong. Yeah, what it does is it treats subsequent input files as having having a type of language, basically. So it's expecting that the following the source file after it, it assumes got HIP code inside and will do a compiler pass to convert the HIP code. And if you don't include it, it will expect to look somewhere else for it. So you need to include that if you've got all your HIP code. There's make files today for the examples. Yeah, HIP cc - help gives some info on this as well. Okay. Yeah, and there's also this HIP programming guide provided in the AMD documentation that provides you some more information as well. I think the main thing that's going to, what we'll do is clarify this as we go with the examples for the rest of the day. And that will help to solve any questions. For now, I just check the schedule we've got. So that's kind of the broad high-level theory I wanted to get to this morning, and I realize there will be details that are not clear to people at this stage, but the examples will help to clarify that. Yeah, I think you can actually not do that programming in CludeLine. There's a default programming environment that's included for you. So just do the Rockham, yeah, do the next three. So I will type this in here. Yeah. Yeah, exactly. Okay. So you'll have some modules to load. So basically during the break now until for the next sort of 20 minutes. So let's say we come back at 20 past 11. We will then discuss the next lecture, which will talk about memory management, and then we'll do a short example. And then we will go into a discussion of running an initial function using this kernel execution model, and that will run us up until lunch at 1 o'clock. Okay, so take a break, everyone. Go get yourself a coffee, and we will start again at 20 past 11. Okay, so in this next section, we're going to start by looking at dealing with these separate address spaces and how we can use HIP to allocate memory and move data between them. And that's going to be the focus of our first example. So we've discussed this concept of you have the host side and you have the device side. You have memory allocated on both, and we need a mechanism to move data between them. And while this may be a bottleneck in terms of performance, we can discuss that more later, but we still need to move between the two. And the CPU, the host side, is controlling this for us. So we have an API for generating this data allocation and freeing it up. So just a couple of things. These for the examples we're giving, these are already included for you. But just if you to write your own code, in order to access this functionality, you're going to need to include the HIP runtime.h. If you wanted the programs to be compiled by the HIP CC compiler. And this contains everything you would need hosted device, but there's also a subset which is just the C++ interface, which does not need to be compiled by HIP CC as well. That's sort of a little bit of just boilerplate almost that you would need to include in these files, and you can see them in the particular examples we're going to look at. But what we really care about in this section is the data. We need to access a pass data round. Data is accessed by kernels must reside on the device itself. It must already be there, or else the program will go and try and find a piece of information it's expecting, realize the pointer is on the host, and initially for what we're going to discuss, that will be an error. There are some protections that can be put in place, which we'll come to later, but ultimately that they have limitations as well. So this is referred to as device global memory or just global memory. It's a little bit unhelpful terminology because you kind of think of everything, but if you're hearing global memory, you're thinking of device. There's different ways to manage the allocation and movement of data between host and device. So broadly two. We have explicit allocations and explicit copies, or we're handling as the developer the movement of the data ourselves. We also, and we'll discuss this later, have the concept of managed memory. But we will look at the explicit mechanism first. So declaration is our sort of standard C++ syntax, sort of data types, and we have some pointers. So in this little example, we have some, we're going to define pointer, a pointer of double called data. This is where our device data is going to be, and we need a reference to that location. So we're going to call hip malloc, and we're going to say, and this is going to go on the device, pass me back the location where you're going to allocate an array of length, n array, and each element is of size double. And then I'm going to, later I can call some kernels to do some work on that data. I've not actually copied anything there yet, so I'm assuming in that comment perform some work. I'm going to do some movement, and I'm going to do some useful work, and then later I'm going to call hip3. Notice that these hip calls return an error code, and we'll discuss briefly and boilerplate in the code to sort of handle these for us. So what this data pointer is often referred to as the host pointer to device memory. It's my reference on the host to that piece of device memory that's been allocated. They have a value, but they cannot be dereferenced on the host. You'll get a program error. I cannot go and figure out what the data should be on another device. I just know I've just got a number sat on the host that tells me there is a location at this address on the device, and it has data sat there. That's I can't dereference that in the traditional sense, and I'll get an error if I try, because it doesn't make any sense to my host. And as I've just said, we'll return to error handling in a moment. But this is a key concept that I have to allocate device memory through a malloc call on the host. The next key thing is I need to be able to do data movement. So I'm assuming I've established some data on the host. I can copy it via hip mem copy. So what this looks like is I have my data, but I've got a pointer that says there's a memory in device, and I've got some host data which I want to move there to that device location, and I've already filled the host data array or the array with some information. I then provide a size. Again, this is going to be a length of my array, n array, times the size of each element of the array, size of double. And then I'm going to provide information about the direction I'm moving the data around. So here is the last element of this function, passing hip mem copy host to device. So I'm telling hip, this is where I want, how the direction of travel should go. I'm then going to do something useful on my device with that data I've now copied over to my device location. And then at the end, I'm going to call hip mem copy again, and I'm going to move this back from device to host. So back from my GPU to my CPU. And you can see here the second calling of hip mem copy has changed slightly. I've now got the destination as the first argument. Then the source is the second argument. And this is the same for both of these, but you need to be careful with the ordering here. I've got to provide the size again. And I've changed the final argument to this function call to now say hip memcopy device to host. So now I'm saying from the device, copy my memory back to my host. So these are blocking calls. They will not return until the data has been stored in GPU memory or an error has occurred. Formally, the API reads, yeah, I have hip memcopy returns hip error of error t. I have some void pointed to a destination. I have a void pointed to a source. I have some size, and I have like the kind of copy, which indicates the direction that I'm passing in. So all these, so most of hip routines return an error code of type hip error underscore t. It's important to check these values against hip success. So we want to make sure that these operations have completed before we move forward. And the error code can be interrogated to provide some meaningful information, like the name or just some descriptive string. In practice, this is usually wrapped in a macro for our own to sort of help us really. And then the examples provided, we will provide an example implementation for that. This has not been included in all the calls in the code snippets in the lectures because we just not clutter everything up. But it's important that you use this in your own codes so that you do get sensible errors and you're able to inspect them. It's particularly important to check the results of the first API call in the code. This will detect any problems with hip, the context, and may avoid surprises later in the program. But like I said, there's a macro provided. Do use it as you're doing your own programming, because if you do hit errors as we go through, then you will get something useful to work from. So I think the next thing we're going to look at is getting on with the first exercise. So what we're going to do in this exercise is move data around, compile our first hip program, get our environment for doing this development on ARCHER2 working, and get to understand a bit about an example program. So this is in, if you've now cloned the Git repository onto ARCHER2 and underneath /work. And this is important, this is on /work, because otherwise the compute nodes won't be able to see anything you compile. You need to look at this, the associated exercise file, exercise.cpp file. And what's provided in the template. I'll show you that template in a second. And there's sections in here which call out to do things to do in some comments about halfway down the file. And they ask you to provide snippets of code to move data around. So in this exercise, the first thing to do is to load a environment to set up the correct modules and the correct compute capability. So this is there's a module called the Cray provide, it's called accelerator AMD, and then GFX90A. We said that we'd have to pass the compiler some information about the particular hardware that we're using, and that module's doing it. There's something similar to say that the CPU's changed as well, and then we've also loaded in Rockham, which provides us access to HipCC for our compilation. First thing you should do is you should try and compile this on ARCHER2. If you've got the modules loaded above, HipCC is hiding inside this macro CC, so don't need to worry about that. What you should do is you should use, there's also a submit script for Slurm called submit.sh. you should build and run this program, and you will get an answer out that says that you've got one of the elements correct. What the program is doing is it is allocating some memory on the host. It is filling that up with some values. It's then expecting you to move that to the device, and then move it back from the device into an output vector, and it's checking that all the movement has happened correctly, and now these two arrays stuck back on the host have all worked correctly. What you need to do is declare some device memory, so call it dx of type double, initialize that device memory, copy the values in your hx or host version of x array into that device array. Then we're not going to call any functions on this data at this point. We're just going to do data movement. So then we're going to call a new copy of that back from the device to the host. And then we're going to free our memory when we're done, so that we don't leave copies of things hanging around. And the program is going to do some automatic checking to make sure that all the elements of our output that we've copied back to the host have got the correct values. Remember to use, there's a macro provided to look at asserting on the errors if there's any error information that comes out from your calls. So there is no kernel being called. We'll discuss that in the next lecture. So the output should match the input, and that's going to be tested for you in a for loop on the host side. Okay, so let's take until about 12 o'clock to 25 minutes to look at that and try and go through this example. There is the that's not what I wanted to do at all. There's the example script for you to edit. On ARCHER2's nodes, and we are here to answer any questions as you go through this exercise. Here's the example area of the to-dos to look at as you are trying to fill out the answer. So one thing I should have just gone into a little bit more detail about is once you've got a piece of code compiling you want to test, you'll need to submit it to the scheduler on ARCHER2. And there are scripts available for you to do this inside each of the different sections of the course. Now, they're very similar, but I realized that for those who may not be used to schedulers, I should make a point of going through this in a little bit of detail. This script is going to set up the necessary parameters so that the scheduler will know how to allocate resource that you need to run on a GPU system. And will run your job, and then when it's done, it will place a output file called slurm-jobid to the local directory you submit this. What I have on screen is the example for script for section 2.1. And the main thing to focus is this top section to begin with. So we give our job some name. We give it some number of GPUs we want to use. In this case, we're each going to use one. We're going to say this is only going to take a minute to run. So run to start running. It will stop running after 1 minute. So that's the amount of time we've requested to run for. We are running on a particular partition of the system. So this is the GPU partition. And we also ask for a quality of service. So in this case, because there's a few of us and we each want to get access, we're going to share a node. We're each going to get a GPU on the node. And as I was saying earlier, we have 4 GPUs per node. So that's the GPU dash shared. We are going to initially run, so that takes care of telling the system what we want to be allocated to us for running our particular job. And then when we want to execute some piece of code, so executable, we tell, we call srun. And in here we've got 2 calls. The first one is to rock of SMI that I showed briefly earlier, which just describes some information about the state of the GPU that we've been allocated. And this is really like a proof of life. Am I on a GPU? Is there a GPU there on the node I've submitted? Is everything working okay before I start my calculation? And then we're going to run our actual .a/a.out file, which is our compiled executable from produced from our C code. So you'll run that, and it will produce an output file called slurm-some numbers. The job ID is assigned to you, and that should appear in the directory once the work has been scheduled and you've got an output. Okay. So rather than say much about that, if you're not familiar with it, those who have used to HPC scheduling systems, it's all very standard. But it is just an extra thing. So when you want to test, this is what you do, and then you may see some errors from that result. Or you may not get the right answer that's being expected. Yeah, if you're getting number of elements 256 and the correct number of elements 256, that's the right answer. Yeah, everyone else, if you managed to get there, let us know. So we I don't want to rush people because we've got time to go through this, but. It could be coming from the ROCm-SMI bit. What you can do is you can comment out that first srun, try rerunning and see if that gives the correct, removes the error. So I don't believe it would work. You might find a way to target other hardware, but I think that HIP just limits itself to mainly providing support for AMD GPUs and limited support for CUDA, for NVIDIA GPUs. This is the kind of the common issue, right? Is what you'd like is a single interface which works independent of the background hardware, be it GPU or CPU, but that has not yet got to a maturity level where it's very performant. MacBook especially and M1 chips are another kettle of fish, and they're not used within the HPC systems. So given that a lot of these are, okay, some of the ones we're discussing today are commercially led, there's not a lot of effort behind targeting that type of kit. That said, we are usually, you have access to your ARCHER2 accounts for the training account for a little bit of time after the course. And there is currently no charging for using the ARCHER2 GPUs. So if there's stuff you want to come back to and test later, or you want to have a think about and retry or refresh your memory, your account will be active for a little while to give you the opportunity to do that. So, or if you have another means of access to ARCHER2 via a project or something, you can access the GPUs for free just by having access to ARCHER2. So between GPUs, what you're going to see is a change in the number of compute units and the memories available. Usually is kind of they tend to increase over time. So when we come on, so what we discussed for now is moving memory around. So what you might see is just more total memory. So you could just have an even larger array or number of arrays you copy over. When we start to discuss how we break up the problem into blocks and how those blocks are sized for optimal use on the hardware, the number of hardware elements, the amount of hardware these could be distributed over will be larger. So the number of compute units tends to increase with time, allowing more parallelism. The other thing that tends to increase is the bandwidth of the memory. So that's kind of the progression to more performance when you buy a newer kit. So the reason you have to pass the compute capability is that the compiler will be thinking about how it distributes the blocks of work we're going to give it in a minute over that available hardware. And you pass a flag to saying, I'm expecting this type of hardware to be available. So you need to change that code for the type of hardware you want to target. So I'm now going to work through this example. If anyone suddenly would want me to wait 5 more minutes, I can do. I'm just a little bit wary of time. Here. Okay. So I'm on ARCHER2. I'm in the work file system. I can look at the modules I've got loaded. And I can see the last few modules I loaded were the correct modules. So ROCm, the compute capability for the GPU module, and to make sure I've got the right compute capability for the CPU in this case. The exercise, it's important to take a minute to look through this file in its entirety. So there's some instructions at the top. And in here, we have got our inclusion of our HIP runtime file, as we said, and we've got some inclusion of some other files, so simple strings, IOStream, and assertions. We've got the definition of our assert macro that we're going to use to deal with errors. We've got some array lengths, which are just being set to 256 for now. And we're going to ignore the bit about num blocks and first block, because that is something we're going to discuss in the next section. We have allocated an array, a pointer to pointer x, which is our input, and h out, which is our output. And we've already calculated the size. So we've said that we want something of size t, type size t, which is called SZ, which is going to be the length of our array, which is 256, and it is going to be each element is going to be of size double. We've set our number of devices initially equal to 0, which we're going to then update. We're going to set our particular device number to be -1. We're doing this that when we probe properties and get information from the system, these get updated. So we can do things like tell HIP to go get the device count and update the value that's at this particular location. So we're getting pass it into the address that's initially set to 0 and tell me the number of devices I've got. And if this is still equal to 0, there's no GPU available, stop and exit. And if we don't, because if we don't have a GPU, then we're not running on the right nodes, or there's something else gone wrong. So we should stop here. So it's a nice little guard initially at the start of our program. Similarly, we can get the device number, which is the property we're going to extract, and there's calls to do that. And we can start to probe some information about these properties. This is what we can do in the program. ROCm SMI we discussed earlier. Sorry, where was I going? The ROCm SMI provides this information from a utility externally from a particular application, but you can probe this sort of information inside using these device property calls. Okay. Now, for the body of what we're doing, we've got, we're going to take our array and assign a pointer from the host, hx. We're going to get a new array of doubles, and the length of that array is going to be array length 256. We do the same for an output. And we assert these have been created correctly. And what we're going to do is we're going to fill hx with 1 times the array index, so just the array location. So 1 all the way up, so, sorry, 0 all the way up to 255. And outputs can initially be set to 0. Okay. And then we're asked to do some things around moving data. And we can then check the results. And checking the results, what we're doing here is we are taking the difference between the output and the input. We've initially set, as I've just said, up here at the top, h out is set to 0. So if I've copied the data over to the device into some device location, and then I've copied it back into h out, then those elements should be the same. We should get 256. Okay. So here, first of all, I need double pointer, which is my device. This is going to be my pointer to location on my device that's stored on the host. So this means that as I operate on data that's external from me through HIP, I know where the location of this data I'm allocating is going to be. I'm then going to call, I'm going to wrap my call in HIP assert to make sure that the error message gets handled from HIP. I am then calling HIP malloc. And I am passing in to HIP malloc the address of this pointer. So what I'm saying is, please update this location, which is a pointer, with the address where you're going to set some data up on the device. Okay, and this allows the host to keep track of this. So here has a reference to this place, and this is going to be a size sz. Okay, and we saw that size was been determined already, and it's been used consistently up here. So I don't reproduce this. I could explicitly write array length times size of double, but I'm not. I'm going to utilize what the rest of my program is going to do. I'll duplicate this. Okay, so that should have inserted some memory into the device. Now my next job is to copy that array from host to the GPU or host to the device. So I'm going to call it insert again. Now I'm going to hit copy. And now it's my destination that comes first, so dx. But now I just pass in dx itself, not the reference. I'm not updating, I'm passing in this value, which is the address location on the device. And I'm also passing in the source of this, which is hx, size, and then also how I'm doing the copy. HIP mem copy, we're going from the host to the device to move the data. Okay. Now I want to move this. It's now sat on the device. I want to copy now to move back. And I'm going to change the location I'm copying back to. So again, hip assert. And now my destination is h out from my source, which is dx. Same size, hit mem copy. Host. Okay. This should be correct. This is it's now going to have fun. Okay, I have a make file here. Yeah, exactly. You've now got 3 copies of the original memory. You've got the local one of the host, the one on the device, and now we've duplicated on the host. But you could see that that's quite a common pattern. If you're going to do something, I want to update process and then get the next iteration of back, I might have to do all these transfers. But I'm going to be limited probably by the size of my device memory, because that's going to be smaller than my host memory. So what you might consider, if you're smart, is you can reduce that to 2 copies, where you say, I have my previous iteration on the host, my starting point, I move that to the device, do some work, move it back to the same location on the host. And then that's my input. But if I'm even smarter, I should try and keep everything on the device. So what I do is actually only move at the start of a set of iterations, and then I'm just going to call things to operate on the memory that's sat on the device. So I do the movement once, I stack up enough work to do, and then I move back, and that helps to drive efficiency. So I get some warnings about certain things which are related to deprecated files, which I'm going to worry about today. I then have a submit script, which I can just look at, which is the same. I can press back submit. You can use SQ --me to look at my currently queuing jobs. I've got something pending. I bet I'm now going to take a while to actually get through the queue, because that's going to be difficult if we are on a training course. If we are typical on a training course, I will have I've made one earlier result that I can show you in a second. Fantastic. Okay, so we're not waiting all day. Hey, okay, no, I am actually ready. Okay, so what I have in this output from Slurm, yeah, I have the same error that I think someone mentioned in the chat. This is just the fact that when ROCm-SMI is ending, it's not ending very gracefully. But I've got 2 calls to srun. I've got first one that's ROCm-SMI. Just tell me, again, it's another check. Have I got a GPU? And have I got some information being replied to it? So I'm GPU 0 out of 4 on this particular node. I've got some temperature, I'm getting some power statistics, some other information. I get some information about the number of properties of the GPU, and then I get my result, which says the elements, the total number of elements in my array is 256, and the total number correct are 256. So saying that we've done all the data movement correctly. Okay. So that's the first example. Now we are going to move on to the next one. If there are people who are still catching up with that, that's fine. We'll make sure there's some time to discuss this today. So if you don't worry if you feel like getting behind. A lot of these exercises build on the previous ones, and there's an example solution in the next thing. So if you're not going to necessarily be reliant on redoing bits that we may still be trying to understand. Okay. So this section, we're now going to talk about how actually doing something useful on the GPU. Now we'll be able to move the data between the CPU and the GPU, so between the host and the device side. You're still seeing the wrong screen, which is annoying. Let me just switch over. Nope. Did. Sorry, give me a second just to sort out my sharing. Right. Okay. So we have this concept in GPU programming where we have kernels, and kernels are kind of our functions for doing work on the GPU. So in many scientific applications, a large fraction of computation effort is spent in kernels. So this is natural, the first target for moving to the GPU is the kernel function. We're going to call it the innermost part of a loop, for example, nested loops. Yeah, so kernels are often associated with loops for which we can distribute independent iterations between threads in parallel. And this is kind of another key concept. So we've got this idea of data movement down. Now we need to discuss about how we're going to, in a sense, manually unroll some loops so that independent threads execute on independent data. And then this massive number of threads we have available, streaming processes we have available, each get independent data to work on, and they can all work at the same time, and they get an increase in performance. So if we have a simple for loop of length my array, and I'm just going to double every element and pass it to a result, each iteration of the loop is independent, and we can safely run each iteration in parallel. If you're used to threading in CPU parallelism terms, you'd run some OpenMP program around this, and it would do that for you. Okay. In HIP, we need to sort of take two steps. We need to write this as a kernel function, which would express the body of the loop. Okay, so this is an example of a kernel called my kernel. I've got some index I, which is my thread index, and this thread index dot x, and this can be kind of confusing. This is meaning index. This is a dimensional element of this object. It's a bit C++y. And we're going to just do a renaming. We're going to call this I, and we're going to run over our array. And each thread is going to get a member of our, each thread is going to be, ID is going to be multiplied by 2 and passed to result. So the global is a so-called execution space qualifier, and it indicates to the compiler that this is an entry point for the GPU to execute. The thread index .x is a special variable that HIP provides to allow us to identify threads. So we can start to address data to be worked on by different threads using this index notation. The second step is to execute or launch kernels on the GPU, and this is done by specifying the number of blocks and the number of threads per block. And we do this with these three-dimensional 3dim objects. And I'm going to say, in this case, I'm going to have one block. So I've got X, Y, and Z for doing it three-dimensionally. For now, we're just going to say there is only one block in total. And there are as many threads in that one block as there are elements in my array. Array. Yeah, so the number of elements array underscore length. So that is convenient, and it's a convenient choice we've made you will not get quite that lucky in real life or in real problems, but in this case, we're making that choice for this example. And then I launch by using this triple angle bracket notation. When I launch my kernel function, I pass this notation in, which tells it how it's going to split. It's going to run this kernel in terms of blocks and the threads per block that you've provided. So this is the execution configuration. And it comes between the kernel function name and its arguments. So we must arrange the product of the number of blocks and the number of threads per blocks to give the correct total number of threads for the problem at hand. So in this particular case, this is only valid if array length is the number of threads per block, and we can see we've passed that in ourselves by hand to this in this particular case. So we've introduced this structure which contains called dim3, and it's very simple. It's just 3 integers. But we'll use as a way to describe the distribution of threads and blocks over a 3-dimensional space. We're not going to look at 3 dimensions. We're just going to keep ourselves to 1 and 2D for these examples, but it's good to know that it does extend further on. So far, we've just looked at a single block where we've indexed over a single list of threads, but we can have more than one block being executed. So if we have a larger problem and we need to access more threads, or we need to divide up our problem into more than one block, we can do this by accessing the block index.x, this, and the block dimension.x. So this is saying I'm going to run through all the threads in a block, and then I'm going to stride my block index up by 1, and that is the dimension of the block, and that's the total number of threads in a block. And those, as you passed in angle brackets, pass that information in, and it's made exposed and made accessible to the inside of the kernel function through these special members. So we could have an execution configuration which we have threads per block.x equals threads per block, and we have the number of blocks equals our array length divided by the threads per block. This is one of these cases where sitting and just having to think about it while doing this next exercise is going to be really helpful. It can get quite confusing because we're talking about very similar terminology repeatedly. And after lunch, we'll come back and start to discuss things around what are sensible choices here and what are the performance considerations for these type of examples. So this is sort of the more general structure about how you'd organize this. So generally, you choose the number of threads per block to be anywhere between 128 and 1024. This relates to the hardware that you're running on. And what you do is you compute the number of, based on that decision, you compute the number of blocks required to cover the whole problem. So in the above, we've still assumed that the array length is divisible by the threads per block. In the example associated with this, we go beyond that and start to consider off by one type issues and give an example of how to deal with that. Is that all I wanted to say here? Yes. Okay. So internal variables in the kernel. So there are a number of internal variables in kernel functions made available by HIP. And they can be used in the kernel to locate a given thread's position in this abstract picture of a grid of processes to deal with. So one of these is the grid dimension. This is the number of blocks you have in total for this particular execution. The block dimension, the number of threads you have for each one of these blocks. You have the block index, which is unique to each block. So this runs from 0 up to the dimension, grid dimension. And you have this in each direction, right? So you can have this block index for an X and a Y, and you can end up building up a grid of these blocks. And then within a block, we have a thread index and a block, and the thread index can run over multiple directions within a single block. And these again run up to the size of the number of threads in a block given by block dim.x. So this can be a little bit tricky to get right about what the hierarchy is here and what you're doing, because you're instead of thinking about the data, you're thinking about threads accessing data independently. It's a slight change of thought process from the CPU side you may be used to. So the other thing we need to do is think about synchronization. The kernel launches are asynchronous on the host. You kick off a kernel launch, on the host side you continue. The launch will return immediately. If we're going to use the result of a kernel execution that's happened on another device, we need to synchronize before we try to use the result of that particular kernel execution. So we have HIP device synchronize that allows us to test that all of the different execution of this particular kernel have completed, because this thread and blocking approach is going to tell multiple different processing units to go do independent work, and that's what this kernel execution is doing, so we get the benefit of the GPU's many threads. We synchronize and then we're safe to continue working. But when we synchronize, we potentially introduce, if different sections of the work have taken longer, we've ended up with load imbalance, this may be we're waiting around a little bit for everyone to get to the endpoint. So there is always a performance hit from synchronization, but you do need it for correctness. So you need to think carefully about when the correct place to synchronize is. Right, so error handling, but now we're talking about not error handling in terms of the execution of the HIP calls to do things like allocate memory and stuff. We're talking about the errors coming from the kernels themselves. So this is quite tricky because the errors occurring in the kernel execution are also asynchronous. This can cause confusion because we don't necessarily have an error getting called back to us in a sensible order. So what we can use is we can assert and we can peek at the last error, and we can assert and synchronize. So the first function, HIP peek at last error, queries the error state without altering it. So it will fail if there are errors in the kernel launch, and the GPU is not available, or there's some error in the configuration. The errors that occur during the execution of the kernel itself will not be apparent until we synchronize at the end. So this could be program error, something we need to debug. So these are your points where you're going to pick up those errors because of this asynchronous nature of launching kernel execution. Okay. So we're now going to go into a little bit of an exercise where we're going to define a very simple kernel ourselves. And what we're probably going to do is we plan to take lunch at 1 o'clock. So I think people are probably going to need 20 minutes at least to look at this, and then we'll review when we return. So what I suggest we do is we will be here to answer questions until 1 o'clock. We'll then take an hour, and then we will come back to start again at 2, and we'll start off with looking at the solution to this. So We're going to start using the solution from our previous exercise, but don't worry, there's a new template in section -2.02 here from the repository with a canned solution from the previous part. So you can either use what you had previously, build on it and do your whole own thing, or you can use the new canned example. You want to write a prototype function. Sorry, let me just. You can, I think what you're asking for is around synchronizing specific kernel calls. I think we will cover this when we come to discuss streams later today, and how kernels can be allocated to different pipelines. But for now, yes, it's a global sync. Okay, so initially, the suggested procedure for this exercise is a very simple kernel that's going to just double the elements in there. So initially, restrict yourself to a single block in the first instance. So you'll need to define and initialize your variables for the number of blocks and the threads per block. Try using one block and threads per block as the number in the first instance in one dimension. Don't go to 2 dimensions just yet. And then try and look at more than one block as the second step of this example. And finally, if you're getting further on, start to consider off by 1 errors, and if things aren't perfectly sized. So you only have an array size of 100 or 1,000. How do you deal with the fact that you can't perfectly chunk this up into powers of 2, or if your array, if your block sizes are powers of 2, things like that. Okay, so let's look at this exercise now until 12. Then we'll take some lunch, and when we come back, we will discuss the output of this. You don't need to, no. You can just pass them directly in. We'll come into this in a bit more detail again later, but there is a very small amount of memory for passing in constants directly by value. So you don't need to do an memcopy explicitly for those, but you're very limited on the amount of space you have for that. I will have a think. I think this was simply because the index is we use int for thread indexes to get the idea it's just a location, not the sizing. I'm trying to say here. Basically, I wouldn't read too much in our decision to use int there for thread index x because that was more. Think about that was more around addressing, just to give a simple example of addressing an array, because the thread index can only be the size of the block, and usually you'd pick something sensibly small. In terms of limits that you can pass to kernels, I don't think you're going to be limited, because what you're saying is there is a size of you've already copied something of whatever sizes that we did use as size t type, and we're copying that over, and that's just some allocated memory. And then what you're telling the device to do is that it's there at this address, now go use it. It's just how you chunk that massive array up to pass the different threads is going to be the important bit. Depending on your block size and your number of blocks, there's no real reason you can't just keep churning. And actually, it's something you want to do. The larger the same piece of the same operation is going to be done, probably the more efficient you're going to do it. Okay, we will return at 2 o'clock. And we will start again with a discussion of performance. Thank you all for this morning. I hope to see you this afternoon.